All right, let's go ahead and get started. So today we're going to be talking about something called equivalence relations. And this is super important because, just thinking very broadly, in abstract math, typically you're going to be looking at some objects, and you need some idea of when two objects are considered the same. So equivalence relations will tell you what is like a reasonable notion of the same. So what we're going to be asking is, when are two things the same? And equivalence relations are like the reasonable notions of sameness. Okay, so let me give an example. So we might be looking at pairs of integers, and typically you would think of the pair of integers 1, 2 as not the same thing as the pair of integers 3, 6. But if you're in the context of rational numbers, so I mean, what is a rational number at its core? It's a pair of numbers. We have that the pair 1, 2 is equal to the pair 3, 6. So underlying this equality, there is some equivalence relation that tells me that the pair 1, 2 is related to the pair 3, 6. Okay, so that's just an example of like two different contexts in which you may consider two different objects to be the same or different. So let me get into the definition of an equivalence relation. So I'm going to let S be any set. Then an equivalence relation on S is a set R of ordered pairs of elements of S satisfying the following properties. So the first one is that for all elements A in S, we have that the pair A, A is an element of the set R. And this is usually referred to as the reflexive property. The second one which is called the symmetric property, says that if the pair A comma B is in R, then so is B comma A. So that's the symmetric property. And then the third and final property is called the transitive property. So if the pair A comma B is in R and the pair B comma C is in R, then so is A comma C. This is in R as well, and this is called the transitive property. Okay, are there questions with the definition? Yeah.
If we have the symmetric property, why do we need them to be ordered pairs?
Yeah, so if you don't, I mean, if you have the symmetric property, then the order doesn't matter, but I guess you could have something that's not an equivalence relation, and then it would be important that those are, yeah. Yeah. So once you have a relation and you know that it's a relation, then the order doesn't matter. Yeah, other questions? So this formal way of thinking about it is a little bit strange. So typically, if R is an equivalence relation, you would write ARB instead of the pair A comma B being an element of R. And then also, usually you use a symbol like this tilde instead of the symbol R. So it would look, so you might say like, for example, you might say tilde is an equivalence relation. And you would write something like A tilde B if A and B are related by the equivalence relation. So this is kind of just like the more common notation that's used, and I think it makes a little bit more intuitive sense than like the setup with ordered pairs. So let me just start off with like a really like simple real life example of an equivalence relation. And I like this because this definition feels really abstract, but this is just like something that you might encounter in everyday life. So I'm going to let S, my set, be the set of students in a dorm. And then I'll let my equivalence relation, so we'll let A tilde B if A and B are roommates. So let's see why this satisfies the reflexive, symmetric, and transitive properties. So what does it mean to say that this is reflexive? It means that a person is their own roommate. So you are your own roommate. And then symmetric. This one would just say that if A and B are roommates, then B and A are also roommates. Okay, so that one is also satisfied. And then the last property is the transitive property. So if A and B are roommates, and B and C are roommates, then we also have that A and C. So let me write this out. Then A and C are also roommates. Okay, so this is just a really simple example to illustrate the idea, and we'll do more mathematical examples as well. But let me just say one more concept related to this. So this will be a definition. So if tilde is an equivalence relation, on a set S, then we have the following notation. So brackets A is defined to be the set of all B in S such that A is related to B. So this set is called the equivalence class. Of the element A. Okay, so this is just all of those things that are considered to be the same as A under this equivalence relation. So in the roommates example, like the set of all equivalence classes would be like the dorm rooms themselves, because each dorm room is the set of students that are all related to each other. So let's talk about a more a math-based example. Are there any questions about this so far? Okay, so this example is going to be about modular arithmetic. Yeah.
So if, like, I have an equivalence class, everything inside that equivalence class is the same equivalence class.
Yeah. So if, so this is a good observation. So the question was, if A is related to B, then is the class of A equal to the class of B? And the answer is like yes by the transitive property, because whenever you have something in here, it will be related to A, and A is related to B, so therefore that element X would also be related to B, and so it would be also inside of that class, and vice versa. Okay, good. Are there other questions? Okay, so this example is going to be about modular arithmetic, so you can take what I'm about to say as a definition, or if you've seen it before, then that is also fine. So I'm going to let s be equal to the integers, and I'll let n be a positive integer. And I'm going to define a relation, and then we'll show that it's an equivalence relation. So we'll let A be related to B if n divides A minus B. Okay, so why is this an equivalence relation? I'm going to give you a few minutes to think about it and discuss, and then we will prove together that this is an equivalence relation. Minus. Okay, so let's discuss this example. So why is this equivalence relation symmetric? Or reflexive, sorry. Yeah. Yeah, so A is related to A if n divides A minus A, which is equal to 0. So this is true. Okay, what about symmetric? Yeah. N times what? Uh-huh. Yeah, so if n divides A minus B, then that means that n would also divide B minus A, which says, so, which tells us that B is related to A. Okay, and then what about transitive? Yeah.
We know n divides, if we're just saying take n divides a minus b and n divides b minus c, we can rewrite both of those as a minus b equals n t, where t is an integer, and then b minus c equals n r, where r is also an integer.
Uh-huh.
And then you can add those two together, and the b's will subtract, and a minus c converts to integers, and so find out n divides b minus c.
Yeah, so basically we can combine these two statements. So what we're trying to determine is if n divides A minus C, and this is just equal to A minus B plus B minus C. And since n divides each of these parts, you can show that n divides A minus C, which is what we needed to show. Okay, so what are the equivalence classes? For example, what is the equivalence class of 0? Yeah. Yeah, so this would be 0 plus k times n, such that k is an integer. So in short, like the equivalence class of 0 is anything that's itself divisible by n. And similarly, like you could replace this if you had an arbitrary a. This would be the a plus kn, such that k is in Z. So we can write the following breakdown of the integers. So Z can be written as the union of equivalence classes of numbers using this equivalence relation. So we need to throw in the equivalence class of 0, the equivalence class of 1, and so on, all the way up to the equivalence class of n minus 1. And then we will have captured all of the integers. So in this way, we can view the equivalence classes themselves as numbers mod n. And if this doesn't make complete sense to you right now, this is going to be an idea that we revisit once we introduce the idea of groups and group quotients. So this, we will come back to this example and examples like it. But are there questions at this moment? Yeah.
What does it mean to union? Like what does that mean?
Okay, yeah, so this is like a set of numbers, right? So this is like, yeah. So these are, each of these is just a set.
Those are the order pairs. Those are the set of numbers that make up
Yeah. So basically all I'm saying is like every integer is equivalent to one of these n integers. Yeah. Okay, so this leads us to the idea of a partition. So a partition of a set S is a collection of non-empty disjoint subsets of S whose union is all of S. So in the previous example, we had this partition of the integers into equivalence classes of individual numbers. And we'll have a general theorem that says that the idea of equivalence classes is really the same thing as the idea of a partition. Are there any questions about this definition of a partition? So you just want to cover the entire set with subsets that are non-empty, and the subsets don't overlap. So you're just chopping up your set into smaller sets. Okay, let's see the theorem about why this is equivalent to equivalence relations. Oop, that's Math 100. So we're going to let tilde be an equivalence relation. I guess this is going to have two parts. So let me break this down. So we have an equivalence relation on a set S. Then the equivalence classes form, what's going on? Okay, so if we have an equivalence relation on a set S, then the equivalence classes form a partition. What mean? The equivalence classes form a partition of S. And the second part of this says that given a partition of a set S, there exists an equivalence relation whose equivalence classes are the partition. Okay, are there questions about the statement of the theorem or anything else so far? So wait, sorry, repeat your question.
So like, are there only a few like equivalence relations where the equivalence classes like form a partition, or do you like is this like totally
Um, there might be different equivalence relations that give the same equivalence classes, I think.
Oh wait, no.
Yeah. But usually, like, what you care about is the like the equivalence classes themselves, and not necessarily like how the individual elements are related to each other. Yeah. Okay, are there any preferences on which one to prove first? No? Okay, so let's prove part one. So let's let tilde be an equivalence relation. On a set S. So we want to show that the equivalence classes form a partition. So what we need to show is the following. So we need the union of all equivalence classes is S. What else do we need to show for this to be a partition? Yeah. Yeah, so we need to show that the classes are disjoint. Let's just call them equivalence classes. Equivalence classes are disjoint. And what else do we need to show? Yeah.
That they're non-empty.
Yeah, so we need that the equivalence classes are non-empty. Okay, does anyone see how to prove any of these parts? Yeah.
You could say that equivalence classes are non-empty because an equivalence class has to be based on some element A, and A has to be in that class since A is equivalent to A.
Yeah, so if we're looking at an equivalence class of some element of A, then, so let's say we're looking at this equivalence class, then A will be an element of that equivalence class. Right, so A, since tilde is symmetric, we always have that A is related to A, so the equivalence class of A must contain A. Okay, good. What about another one? Yeah.
And they are always going to be disjoint because if they even share with one element, they're going to be the same set. They're going to be the same equivalence class.
Yeah. So let's do this one out a little bit. So let's suppose that C is some element that's in the equivalence class of A intersected with the equivalence class of B. And then what we want to do is show that, in fact, then these two equivalence classes must be equal. So that would mean that our equivalence classes are either equal or they contain no overlap, so they're disjoint. Okay, so if C is in both, then that means that A is related to C. Or rather, let's do this. So we'll show So whenever we want to show that two sets are equal, one way we can do that is to show mutual containment. So we'll show that the equivalence class of A is a subset of the equivalence class of B, and vice versa. So we'll let X be any element of the equivalence class of A, and then we'll show that that X will also be an element of the equivalence class of B. So then X is related to A, and A is related to C because C was in the intersection of both classes. C is related to B because B was in that equivalence class. So we have, by transitivity, that X is related to B, and so X is an element of the equivalence class of B. Okay, so that shows that the equivalence class of A is contained in the equivalence class of B, and we could use the same argument to show also that B is a subset. The equivalence class of B is a subset of the equivalence class of A. Okay, so that shows that the equivalence classes are disjoint. Are there questions? Do you have okay, so let's see why the union of all of the classes is S. Why is this the case? Do you have a... Yeah.
I think there are kind of two things that have to prove. I think first, in every, kind of by definition of an equivalence class, every element of S is in one of the equivalence classes, is an equivalence class, and there also isn't anything outside of S in here because the equivalence class is only defined outside of S.
Yeah. So, okay, good. So given any A in S, we have the equivalence class of A and A is in that class. And furthermore, an equivalence class, sort of just by definition in the way that we set it up, is a subset of S. So these two together would tell us that the union of all equivalence classes is S. Okay, good. So in summary, we've done one part of the theorem. So we've shown that if you have an equivalence class, if you have an equivalence relation, then the equivalence classes give you a partition of the set. So let's do this other statement. I'll just copy it so that it comes with us to the next page. Okay, so given a partition of a set S, there exists an equivalence relation whose equivalence classes are the partition. Let me draw sort of a picture to illustrate this. So let's say this blob is our set S, and I've broken up the blob into some partition. And what I want is that given any 2 points, let's say A and B, as long as they're in the same portion of the blob, I want the equivalence relation to relate those two elements. So does anyone see a way to define the equivalence relation? Yeah. Yeah, so we'll say that A is related to B if A and B are in the same part of the partition. So like all this is like the dorm room equivalence relation. Like this is exactly the same as that. So why is this an equivalence relation? So I guess we have to show that it's an equivalence relation and that the classes are the partition. And then we also have to show the classes. B. Okay, so why is this an equivalence relation? Yeah, so I mean, like, reflexive is super easy. A is in the same part of the partition as itself. So I think this is convincing. And then if A is related to B, then we also need to have that B is related to A. And I think this is also clear, right? And then is transitivity clear? So if A and B are in the same part of the partition, and B and C are in the same part of the partition, then that also means that A and C are in the same part of the partition. I think this maybe this relies on the fact that the portions of the partition are disjoint. Right, because if you had B and C over here, then A and C would not be related, but this situation can't happen because B can only be in one part of the partition. Okay, and then why are the equivalence classes equal to the partition? Yeah.
If you have some element A, and you have the equivalence class of A, then that class is going to be all elements of S that are in the same partition as A.
Yeah.
That's just the partition itself.
Yeah, so this this equivalence class would be equal to that part of the partition. I didn't write down notation for the partition, so let me do that now. So I'll say that this is usually also like side note about notation. So this symbol, this like U means union, and if you use like a square U, then that means that the things you're unioning over are disjoint from one another. So let's say this is over some I in some index set, and then we're going to call the parts of the partition P sub i's. Yeah.
So like you can only use that notation if you've already proved that everything is disjoint. It's just like indicating that.
Yeah, yeah. Okay, yeah, so this would be equal to one of the P sub i's, and we will get all of the P sub i's just as you arrange A over the entire set. Okay, so that concludes the proof of the theorem. So hopefully that helps you understand a little bit about what equivalence classes are, because now you have a way to picture what they're doing to a set. So let me return to the example that I opened with at the beginning of lecture. So I was talking about pairs of numbers and saying that that there was an equivalence relation that basically gives you as the equivalence classes the rational numbers. So let's briefly talk about that. So let's look at the integers crossed with the integers, and I have to take away 0 because the second coordinate is going to be like our set of denominators, sort of. And I'll define an equivalence relation in the following way. So this is going to be our set S. So I'm going to say that A comma B is the same as C comma D if A times D minus B times C is equal to 0. And I want you to think about, why is this an equivalence relation? And then also, I want you to think about the equivalence classes. And my claim is that the class of an element AB, you can think of this as being the rational number AB in Q. So this, maybe this equal sign comes with like some air quotes, but so why is this true? Why are the equivalence classes equal to the set of rational numbers? So I'm going to kind of just end on that note, so you can stay and discuss if you like, but we only have 2 minutes left, so I won't go through the whole example, but feel free to stick around and talk to each other or ask me about this. Hey. Hey. entire, I think they probably mean it. So if I had like the entire real life, is there like a subset of this that like represents all of the real numbers up to the equivalence relation?
I mean, it makes sense for integers for you could just choose like 1.
Yeah, so let's say we take 1.
That doesn't
Then that's like all we need.
yeah, but that doesn't fill in stuff for like fractions. So
Yeah.
you need like
You're driving me crazy. Okay, so if you have like, say you have like 7.893511, you know, have it. What do you need to know about this number?
you just need to know like like what how much of a fraction it is up to 1 and then like 7, right?
Yeah, because this is like, okay, so this is the same thing as like, we can just kill the 7. So this is the same as like 0 point whatever.
Right. Oh, so it's like a triple?
Yeah, so really all you need to know is like those numbers. And those like capture all of the real numbers up to the equivalence relation.
Okay, and you don't even need 1 because you can just use 0.
Yeah, if you include, yeah, see, I could have done it the other way. But then like, so even like, maybe a better picture, since this 0 is equal to 1, then really what this is like SR, because I've moved those 2 points.
Oh,
Yeah.
that's really cool.
Yeah.
Thank you.
Sorry. Oh yeah.